In previous lectures, we discussed about dimension reduction of data points. Now, I will be discussing another issues related to data representation, which is called sparse representation. So, let us understand the problem statement involved in this particular issue. Consider we have a dictionary of n elementary ND vectors. We call it dictionary. It is something like set of basis vectors, but in the set of basis vectors, we would like to have only those basis vectors which are sufficient to represent data. But here we consider a redundant set of basis vectors. That means, we have more number of basis vectors and a few would be only required to represent a data. And the term what we will be using instead of set of basis vectors, we will be calling this particular collection as a dictionary, as if you have lot of vectors, redundant vectors, and conveniently you would like to use them for representing your data or signal. Now, the elements of this dictionary, they are called atoms, that is the terminology we will be using. And you consider any arbitrary vector, n dimensional vector. So, the problem here, you have to compute the best linear approximation using a subset of D as basis vectors. As I was mentioning that D is an overcomplete representation of basis vectors, which means there are many redundant vectors and it is not required all the vectors should be used for representing data. So, the linear combination of the subset of D can be expressed mathematically in this form. As you can see that x is your input vector, it should be very close to a linear combination which is given as a multiplication of each dictionary elements with a scalar constant a j and sum of them, and d j's are the elements of that set which has been considered for representing x and which has to be a subset of this dictionary. And it is as you know, in an n dimensional space, it is sufficient if you have n independent basis vector, n linearly independent basis vectors, and then it is sufficient, you can use them to represent any arbitrary vector x. So, here you have an overcomplete representations and you desire that this number should be less, and that is the sparsity we are considering, that you require a few basis vectors only from D which should be sufficient to represent x. You do not require n basis vectors, it should be much smaller to n, and that is what we are trying to achieve using this kind of representation. So, the idea is that this number of atoms should be minimum. So, for the particular problem statement, you would like to have that S subset whose cardinality should be minimum, and also reconstruction should be as close as possible. So, it is an approximation. So, to make it more precise in that case, how close it is, first thing it could be exact reconstruction. So, you find out the minimum S which will give you the minimum cardinality of S, a minimum number of atoms which will give you the exact reconstruction. So, this could be a problem and it is a very precise problem statement. Or what we can do, we can keep the number of atoms fixed, say what is the best representation, that means how close, that should be the error between the representation approximation of x and x should be the minimum original value. So, it should be very close to that. So, to summarize this problem, it is a problem of approximating a signal with the best linear combination of elements from a redundant dictionary. It should give some optimal or near optimal representation. The computation should be fast. These are the desirable properties, and the dictionary also should be optimal. And sometimes there are joint optimization problem that you would like to have also a dictionary of with an optimal size, so that gives also the optimal sparse representation of data. So, to elaborate this optimization task, we can consider this mathematical formulation that we have to minimize the approximation error using L2 norm. You know, L2 norm is basically it is the Euclidean distance or in the n dimensional space, and this you are using this and also using m terms. So, you have a dictionary D which is a set of di's, each one is an atom, and this is L2 norm, this considers L2 norm. So, just to show you what is meant by L2 norm, suppose you have a vector is represented as say x1, x2 to xn. So, L2 norm is defined as root over x1 square plus x2 square. So, this is the definition. So, you consider this is an error vector x minus of linear combination, and this term has to be used. So, the problem here is that you should get that set of coefficients, and the total number of atoms should be exactly equal to m, so that you get the minimum error, minimum L2 norm of these values. So, this is explaining the corresponding components of this expression. This is the data vector and this is the linear combination, and it gives you the fixed number of atoms, that constant. Suppose I have given you an set of atoms which is a subset of the dictionary D. Now, how can I get the best reconstruction which in terms of linear combination of these atoms for any arbitrary x, for any arbitrary vector x? So, we can see that we can formulate easily the least square error optimization problem. We construct a matrix B. So, once again B relates to that set of basis vectors, and each element of S is considered to be a vector, a basis vector. So, this B is formed in this way. So, each column vector of B is a corresponding atom of S. So, the dimension of B should be n cross m. As you know that dimension of each vector, each element of D is n, small n. So, each column vector is of small n, that is the dimension. So, number of rows would be n, and since there are m elements, m atoms, so you will have m columns. So, the dimension is n cross m, and if you consider the linear combination of these atoms, which can be conveniently represented as in this form. So, here A1, A2, these are all scalar quantities, these are all scalar, and you are multiplying A1 into di1 plus A2 into di2, like this you proceed, and you can represent in this form. That is how you get the linear combination. So, this linear combination can be represented, and this is this set of coefficients or this column vector, let me denote it as y, and this linear combination can be represented as the multiplication of B and y. B is the set of basis vectors, as I mentioned, formed from the dictionary, where each basis vector is the column of B, or dictionary elements of is the column of B, and y is the corresponding set of coefficients or list of coefficients with respect to each atom. So, y is the representation of x given this dictionary B. So, y is the transform of x, and this should be sparse. We would like to have y as sparse as possible. So, how to get the best approximations for m elements? As you can see, this is nothing but you can convert it to a least square error estimation, because what you can do, you can minimize, here B is given, x is given, what you have to find out? You have to find out y. So, minimize this norm x minus by square, and that y will give you the optimal representation of this particular element, representation of x with respect to these constraints. So, we know this solution, number of times we have we did it, because here once again just let me put it. I would like to get a close approximation in this form. So, what we can do? We can multiply B transpose, and then y can be written as B transpose B inverse B transpose x. So, this is a representation, this is a solution of this particular problem. So, this is how you can get y out of this process. So, the problem here is that if I give you S, then use the least square error estimation method to get a representation y for particular x. But which subset you should consider? Which list m atoms you should consider from the dictionary? That is what is the basic problem. If I know that this set of atoms will give me the minimum reconstruction, then or sparse representation, I can easily get the solution. So, there are various approaches to select those atoms which will derive this kind of sparse representation. Now, these approaches are called pursuit approaches. So, two major approaches, one is orthogonal matching pursuit, another one is basis pursuit. In orthogonal matching pursuit, or in short we call it OMP, here the algorithm is an iterative greedy algorithm. What it does, it selects at each step the dictionary element which is best correlated with the residual part of the input vector. We will see what does it mean. That means, what it is doing, it is successively refining the representations. It is like successive approximations. You take the original vector x or input vector x and find out the basis vector where the component is maximum. That means, that vector is representing the maximum part of the signal. So, you choose it in your dictionary element, and that is your representation itself. So, that vector and the component. Then next time what you do, then you subtract the represented part already, what is being done by that vector, that is called residual. The next time again you carry on the same operations with residual. So, with residual again you find out along which directions you are getting maximum component, then you add it to your dictionary, use it for least square error estimation, use it, as I mentioned, that if I give you a set of basis vectors, I can easily derive what is the best representation, best linear combinations which will represent the corresponding vector. So, use that technique to derive the best representation, and continue doing it for m atoms, m number of times, or as long as you want to represent the data. So, it produces a new approximate by projecting the residual onto the dictionary elements that have already been selected. What I described, that is mentioned here, that every time you are considering residual part of the input vector, you project it on a particular vector dictionary element which has not has been used already, and the dictionary element which is giving you the maximum value of projection, that should be included into your set S, and use set S to represent the efficient representation. It extends the trivial greedy algorithm that succeeds for an orthonormal system, that is the characteristics. The other approach which is called basis pursuit, it is a more sophisticated approach, and what it does, it replaces the sparse approximation problem as a linear programming problem. I will elaborate that problem statement. So, before describing the orthogonal matching pursuit algorithm, let me describe a similar algorithm which was suggested before orthogonal matching pursuit. It is simple matching pursuit algorithm. So, the idea is here that at every time you just look at only those elements of the dictionary where you get the maximum residual component, and use that element itself to represent the vector. So, it is minimize the approximation error using L2 norm, using m terms, that is the objective, and you are considering that at kth iteration, since it is iterative process, you have residue representation as R k and approximate representation of the data or signal as A k. So, the initialization is that your whole signal or whole vector, input vector itself acts like a residue, R naught is equal to x, and so far you do not have any approximation which is 0, which you need to do. Then at every step, every kth step, what you are doing, as I mentioned, you are finding out the direction, finding out that element of dictionary where you get the maximum projected component. So, this is the residual at this stage. So, what is the projected residue along this particular dictionary element, and then consider only that dictionary element where this value is maximum. So, you choose that dictionary element, say I star is that index. So, now use it for representing the signal. So, this would be your magnitude and this would be your direction of the vector. So, now the signal which is represented by A k, that is approximate representation at the kth iteration, it should be incrementally it is representing that approximation. So, with previous approximate representation you are adding this vector as I mentioned. So, this is the magnitude part of that vector, which is the component what is there in the residue, and this is the direction of the vector. So, di star gives you the vector itself. So, you add it with A k minus 1, that is previous approximation, and then you get the corresponding approximate representation. So, now the residue R k at kth step would be this, and this residue will be for the next iteration, use this residue once again for finding out the next next part of its representation approximations. So, you repeat this process till you get a good approximation, and you should note that this is equivalent to this computation. So, I can subtract the approximations, what is the approximate representative signal from the total signal, then also I get the residue at this stage, or I can incrementally build up the residue. So, earlier I had residues till k minus 1 stage, and out of that already this part is accounted, that means the R k minus 1, this residue, the projected component of the residue along di star, it has been already taken care of, it has been transferred to the approximation part. So, the residue part gets reduced. So, slowly residue is reducing and it is tending to 0. So, when it becomes 0, it becomes exact representation. Otherwise, the whatever part is there, that is the approximation, still that error of representation will remain as a residues. Now, problem of matching pursuit, as you can see in this process, it may select the same dictionary element again and again. So, we have not put any restriction, we are searching throughout the whole dictionary element itself. So, if your residue is still, so at some stage once again you can get the same dictionary element, and if I am trying to restrict for m terms, so I have to also keep a separate count that how many elements are presently taken care of in my representation of the signal. In orthogonal matching pursuit algorithm, we take care of that factor, so that the elements of the dictionary, they do not appear repeatedly. So, because we will be performing a least square estimation, so your residue will be always orthogonal to the selected set of dictionary atoms. So, that is the property we can ensure by doing least square error estimation. So, here the process goes like this. First you have to initialize it. So, you have these two atoms, R naught equals x and A naught equals 0. So, this is the same initializations, and at kth step, and also you are considering the set which will be including the set of dictionary elements which will be reconstructing the signal. So, at kth step, first we find out that what is the direction along which you get the maximum component of the residue, and in the same way what we did for the matching pursuit, and once you have chosen that, then you put it into the set of atoms what would be used for representing the signal x or the input vector x, and we would like to find out the best linear approximation. There we will be using the least square error estimate method. So, that is the difference from matching pursuit. But by doing it, what you are ensuring that all the atoms selected in the set S, that means Sk at kth iteration, all these atoms, they are orthogonal to the residue Rk at that stage, kth stage residue. So, the residue is computed like this. So, I mentioned that this minimization can be performed with standard least square techniques. So, this is a residue, and this residue we have ensured through this step by enforcing least square error estimation that Rk is orthogonal to all the elements of Sk, and that is why in the next iteration you do not require to bother about finding out the elements. So, in this case actually I should have written J belongs to this set of dictionary D minus Sk minus 1. You are only choosing those elements which are remaining elements of the dictionary which are not within the Sk, and you go on doing these things till mth terms for best m terms approximation. This is what is orthogonal matching pursuit. So, as I mentioned that OMP selects an atom only once, as the residual is always orthogonal to the selected set. Basis pursuit problem is different from orthogonal matching pursuit problem. It minimizes the approximation error using L1 norm, and that too it is L1 norm on the coefficients of representation, that means coefficients of the linear combination, and it gives you a convex function, and hence it can be minimized in polynomial time. And you can see that this is the problem statement, as I mentioned, that you are trying to minimize the sum of coefficients representing the signal, and by that you will be achieving a sparse representation. And there exists no different approaches to solve this problem. We are not going to discuss any such solution. It involves also mathematical, complex mathematics to argue on those solutions. So, in this particular case we will be considering only orthogonal matching pursuit for representing, for getting a sparse approximate representation of a signal using a dictionary. So, let me solve some exercises to elaborate these computations. Let us consider this problem that you consider the set of basis vectors. There are 3 set of basis vectors, and you have to show that they form an orthonormal set of basis vectors. And then if I have given you this orthonormal set of basis vectors, you represent a vector 1, 2, 3 as a linear combination of this above set. Now, for checking orthonormal set of basis vectors, what you can do, you take any pair of vectors, and if you perform dot product, then it should be 0. So, any pair of vectors, different vectors, and magnitudes of these vectors, all the magnitudes of these vectors should be equal to 1. So, and that is how we can test, and you can see here also, just typically let me give you one example. Suppose I have taken this vector and say this vector. So, the dot product of this vector is 1 by root 3 into minus 1 by root 6 plus minus 1 by root 3 into 1 by root 6 plus 1 by root 3 into 2 by root 6. So, you will see that these are the 2 negative terms. So, it should be minus 2 by root 3 into root 6 plus this is 2 by root 3 into root 6. So, this should give 0. And in this way you can choose any pair of vectors and you can find out their dot product is 0, and if I take the magnitude, so take the magnitude of any of these vectors, say magnitude of this. So, magnitude means the square of minus 1 by root 6, which is 1 by 6, plus square of this 1 by 6 plus square of this, which is 4 by 6, and you take the root of that, and which is root of 1 plus 1. So, this is how you can show that this is orthonormal basis vectors. Consider the other example, other exercise. That means how to represent any arbitrary vector, a vector 1, 2, 3 as a component. So, what you are doing, you are taking the component of this vector 1, 2, 3 along all these orthonormal basis vectors, along the basis vectors. So, this is the component 2 by root 3, this is the magnitude 2 by root 3 along these vectors, and 7 by root 6 along these vectors, 3 by root 2 along these vectors. So, finally, linear combination can be expressed as you can see that this provides you the coefficients of linear combinations. All these dot products, they are providing you the coefficients of these linear combinations. We have discussed this theory in my lecture in image transform. So, you can revisit that lecture once again. So, here the point is that if I give you an orthonormal set of basis vectors, then you do not require to do any complex operations what we discussed for matching pursuits. Simply you take the dot products with respect to any arbitrary vector, and that value itself will give you the coefficients of the linear combination. Let me take the other example. If I consider a dictionary in a 3D space consisting of these atoms. So, you have seen there are 4 atoms there in the dictionary of 3D space, and we can show that they are all linearly independent atoms. So, which means it is a over complete set of dictionary. As you know, in 3D space 3 linearly independent vectors are sufficient to represent any arbitrary vector. So, derive the best representation of the vector 1, 2, 3 using 2 atoms of the above dictionary following orthogonal matching pursuit. That is what is our problem statement. So, we will apply the orthogonal matching pursuit algorithm. First, selection of an atom. So, find out the atom along which you get the maximum dot product value or component value. So, you take this dot product of these 2 and you get 6, and that is the maximum. You can check over other 3 atoms also, it is the maximum. So, you select this atom for the representation, which means this is the magnitude and the direction is 1, 1, 1, that is a vector. So, the residue would be 1, 2, 3 minus 6, 1, 1, 1 transpose. I am, for the convenience of representing in one slide, I am using row vectors representation of this particular vectors. So, your residue at this stage becomes this vector. Now, the second selection. So, second selection means now which atom? From the remaining set of atoms, once again you perform the dot products with each of them, and you can observe that -1, -1, 1 that is giving you the maximum value of these dot products, and that value is also 6 here. So, now you have this in your dictionary, you have 2 atoms 1, 1, 1 and -1, -1, 1. So, use this dictionary to obtain the best linear combination representation of the vector, and you can use what you can do that you form that best set of basis vectors B as we have done. So, this is what is B, and this is what is A in our representation, and this is the input. This is what was X in our representation. And then here actually there is some confusion of this. We are considering this value is A, this matrix is A here instead of B. So, now you get this is a solution. So, to compute that A transpose A inverse you can compute, and you can compute the linear combination, those coefficients x and y using the this pseudo inverse. By using pseudo inverse, you can compute it. So, finally, your linear combination of the dictionary elements, the best linear combination using 2 atoms for 1, 2, 3 is given this. So, this is your required solution. These are linear combinations that you are getting. So, with this, let me stop at this point, and we will continue this discussion for sparse representation in the next lecture. Thank you very much for listening.